Hi everyone, welcome to the first recorded lecture for Geography 322. This is lecture 9, and this lecture focuses on chapter 7, watershed scale processes. And there's going to be two parts to lecture 9, parts A and B. This is part A, and it focuses on the first three topics that you see here on the outline. To start, I just want to make sure that everybody understands what a watershed is. A watershed is a unit of land that delivers surface water runoff to a specific drainage network, to a specific creek or river. And it's defined by topography. It's all of the land surface that slopes down towards that particular stream or river. That's what the watershed is. If the land slopes down towards a different stream or river, it's a different watershed. If we look at a topographic map like this, we can see a watershed. And right here in the middle of this topographic map, we see the watershed of Allen Creek. If we want to define the watershed, we're going to start down at the mouth of Allen Creek, which is down here where Allen Creek joins the larger creek. And we can see a ridge line running along the south side of Allen Creek that divides hill slopes that slope down towards Allen Creek from hill slopes that slope to a different nearby creek. And that ridgeline goes all the way around Allen Creek. We see it on the north and south side. So if we want to define the watershed of Allen Creek, we're going to start down here at the mouth, and we're going to start up this ridgeline. So here you can see the watershed boundary starts from the mouth and goes up onto the ridgeline on the south side of Allen Creek. And then we want to continue along this ridgeline defining the watershed boundary, always staying on the highest point of the land that is the boundary between the slope to the north and the slope to the south. And then if we draw that line all the way around Allen Creek, you can see this complete watershed boundary for Allen Creek. And that watershed boundary is also a drainage divide. It divides the land surface contributing to Allen Creek and from the land surface contributing to the creeks to the north and south. Just to clear up terminology a little bit, these three terms, watershed, drainage basin, and catchment, are used to refer to the same thing. Watershed is what Americans call drainage basins. Catchment is a British term for drainage basins. So you'll pretty much see drainage basin or watershed in our textbook. As you remember from Chapter 1, the watershed is an open system. Precipitation comes into the watershed from outside. It's delivered to the watershed as precipitation. It flows down the hillsides. It gets into the groundwater. It flows down this drainage network, and it leaves the watershed. So water, incoming precipitation, is mass that's brought into our open system and exits our open system. The watershed's also an open system in terms of sediment. Now, watersheds don't gain a lot of sediment from external sources very regularly, but they do regularly give up sediment. Sediment leaves the watershed, so the sediment is an open system. The watershed is an open system in terms of sediment. The drainage network transmits that sediment downstream and transports it out of the watershed. One of our main focuses in geomorphology is where is sediment coming from and where is it going to, and where does it pause in its route out of the watershed. So if we have erosion going on in hill slopes, sediment is leaving hill slopes and is moving down towards the drainage network. Not all of that sediment is going to leave the watershed. Some of it will get stored temporarily within the watershed. If we have a storm event going on and sediment starts to be mobilized, of all the sediment grains mobilized during that storm event, some of them will leave the watershed as runoff as that discharge goes downstream and out of the watershed, but some of them will be deposited in various positions within the watershed, and we're going to look at that a little more closely in the next slide. Here's a watershed with its headwaters snow-covered, and then some parts of the middle of the watershed with hills contributing, sloping down into the valley, and down the middle of the valley runs a floodplain with a river channel in it and various land uses. So we're going to look at this watershed and think about where sediment is coming from, what are the erosion sites, and where might sediment be stored temporarily, and we're also going to think about the sediment that will be transported out of the river channel out of the watershed along the river channel. Here are the major erosion sites in the watershed. And these aren't all the sites, these are just examples of where these processes might occurring. So some of the hill slopes may experience mass movement, some of the steeper slopes may be mass movement sites, and that mass movement will move down the hill slope and towards the valley floor. The mass movement sites, of course, could be on this side of the valley, there could be mass movement sites on the other side of the valley, really anywhere in the upper part of the hills. In addition to mass movement, we're going to have some sediment that is mobilized by water flow. So we're going to have some hill slope erosion. And again, that's going to start near the ridgeline, move down the hill slopes towards the valley floor. Some of the hill slopes have tributaries, small creeks flowing off of them, and those tributaries are carrying sediment, and they're carrying sediment down towards the valley floor also. In addition, as the river flows down the main part of the valley, it will erode its riverbanks in different places, here and maybe up here and maybe up here. And so that's a fourth source of sediment that's being eroded and added to the river flow. And finally, this sediment yield is going to be carried out of the channel. Some of the sediment that's eroded is going to be carried out of our open system and outside of the watershed. But not all of the sediment that's eroded will leave the watershed. Some of the sediment that comes off the hill slopes in the form of mass movement or hill slope erosion may collect at the base of the hill slopes and not get to the stream channel. So some of the sediment coming off as mass movement may end up as mass movement deposits down at the foot of the hillside. And some of the sediment eroded by water through hill slope erosion may be deposited as colluvium at the foot of the hill slope. And tributaries that are experiencing erosion and transporting sediment down towards the valley, some of them may deposit that sediment in an alluvial fan at the mouth of the tributary. Some of this sediment will go on into the river channel from each of these sources, but some will be deposited in local storage sites. As the river transports sediment downstream, some of that sediment will be deposited by the river channel out on the floodplain. So the floodplain itself is another temporary storage site. And of all the sediment that's mobilized by erosion, whatever proportion of it doesn't get stored is the sediment yield, the sediment that's leaving the watershed down here at the mouth of the watershed. So here are the processes of eroding sediment from the uplands that we've been talking about. Mass movement, and of course there's a range of mass movement types from the very slow-moving creep and heave through flows and falls and slides that happen faster. And then the second major group is the water processes, or the diffusive processes that were discussed in Chapter 5, where incoming precipitation hits the soil and rain splash dislodges soil particles and takes them down slope, and the rain also becomes thin sheets of water that move down slope as sheet wash that transports sediment, and then finally those sheets may coalesce into little threads of water like miniature streams that are rills that eventually join up and become bigger gullies. Erosion processes and the rates of erosion aren't the same everywhere. They differ from one watershed to another. They're different in different regions around the world. So this slide categorizes what are the factors that determine the rates and the dominance of different processes of upland erosion. If we start by looking at mass movement, geologic controls are really the most important. Are we in a geologically active area where there are tectonics going on? In that case, we tend to have high relief and a lot of steep slopes, and that's a major factor in producing mass movements. Also, just the rock type. Some rock types are stronger and more resistant to mass movement. Some rock types or sediment types are much more susceptible to mass movement. Beyond the geologic controls, moisture and climate do play a role. We know that water lubricates a lot of mass movement and triggers a lot of mass movement. So wetter climates tend to have more mass movements than dry climates. And also vegetation cover plays a role to a certain extent. But the role of vegetation cover and human impacts in causing mass movements is not as important as geology. If we go on and think about water erosion processes, there are really three factors that are all almost equally important. And one of them is slope steepness. So again, the steeper the slope, the faster the rate of erosion, if all other factors are equal. Second one is moisture and climate. Again, rainfall is the major driver of erosion here. So wetter climates have more water coming in to do erosion than dry climates. But the third factor is also really important. What is the vegetation cover? So if we have a wet climate with a lot of vegetation cover, the vegetation cover protects the soil from water erosion. If we have kind of a semi-dry climate with thin vegetation cover, when it does get some rainfall, it's going to be fairly susceptible to erosion. So vegetation cover is really important in water erosion, and humans have modified vegetation cover. So we might be in a wet climate, but the slopes are bare because humans have cleared the vegetation off the slopes. Then we're going to see high erosion rates. This slide shows a really classic graph in geomorphology that pulls together these principles. It was published in 1958, so it's really pretty old, and it was kind of unlimited data, and we have more data now, and it probably should be redone systematically. It's based on measurements of sediment yields in rivers in the Great Plains in Midwestern U.S., so sort of from the Mississippi River west to the Rocky Mountains. And these are low relief watersheds. They don't have mountains in them, so what we're looking at is mainly water erosion. And if we look at the graph here on the left, the horizontal axis is labeled effective precipitation. And so effective precipitation means how much rainfall comes down and then how much is left after evapotranspiration to actually run off across the landscape. So it takes into account the dryness of the climate. And the vertical axis of the graph is annual sediment yield from low values down here at the bottom up to high values up at the top. And we're going to have to consider watersheds of different sizes, so this is all normalized for drainage area. It's not sediment yield for the whole watershed, it's sediment yield per square kilometer area in that watershed. So what we see on this graph is at the left side of the graph where precipitation is low, the arid regions, and you can see the vegetation types are labeled here up the top. So desert vegetation occupies the left side of this graph. The sediment yields start at very low values in arid regions, and as we move into wetter and wetter regions and into semi-arid regions, the sediment yields increase very rapidly. So sediment yield is low in arid regions because there's very little vegetation cover, but in these real arid regions down here, there's very little rain, so there isn't much sediment yield. As we move to the right and we get slightly wetter, we begin to have rain events. The vegetation cover is still pretty bare, so we have rain events on bare land, and we have high rates of sediment yield because of the lack of vegetation cover. So the semi-arid climates are sort of this part of the curve right in here. And then we get into subhumid landscapes where there is some vegetation cover. We get into grasslands where there is relatively continuous vegetation cover over the land surface, even though there aren't any trees. So we're in wetter climates here, so we're getting more rainfall events, but we have more vegetation cover, and so the sediment yield starts to decline. And as we get into wetter and wetter climates, we're in thicker and taller grasslands, and finally we get to the grassland forest boundary. And so as we go into wetter climates, even though there's more precipitation events, there's more water to erode the landscape, that land surface is so thickly covered. As humans developed intensive agriculture and also developed ways to harvest forests and use them for products, we've dramatically changed vegetation cover on Earth. And there's been a huge impact in sediment practices. So you can imagine the beginning of agriculture, the footprint was pretty light, and then over thousands of years, we developed new agricultural techniques. Agricultural became more intensive. And then by the Industrial Revolution of the 1700s, 1800s, we began to develop machinery to help us do even more intensive agriculture. So by late in the Industrial Revolution, agriculture and forestry were both very intensive. And it's been estimated that sediment erosion was 10 times to 100 times higher in the early 20th century, well into the Industrial Revolution, than it was under natural vegetation. By the early 20th century, however, we became concerned about these high sediment yields and particularly soil erosion and the loss of soil fertility. And so a lot of conservation practices have been developed since the 1930s, particularly in the US. In the drought of the 1930s, the Dust Bowl, as a society, we became very concerned about soil loss, and we started developing conservation practices. And conservation has been very widely implemented in agriculture since the 1930s and moving on through the 20th century. So today we have decreased those sediment yields. They are significantly lower than they were at the worst of it. And down at the bottom here, I'm just showing you some slides that are examples of how agriculture agriculture and forestry have changed the landscape. So here on the left, we're looking at a slide from the tropics in Madagascar, where tropical forest has been removed, and you see a lot of gullies and erosion going on in this landscape. You see bare, exposed, red tropical soils. You see landslides that have happened in this landscape. So this was forested. Forest has been removed for human use of the landscape for production, and we see these exposed erosion features. So the legacy
on this
of these
slide
land
over on the right,
recorded in our landscape. You can go out and look at floodplains
US
and see the effect
a lot
of
of these soil
agriculture.
conservation
And
practices
this
have been
photo shows
implemented.
a riverbank
So we
in
see
Wisconsin
strip cropping
that
rather
has
than
this evidence within it.
running rows
As we
up
look
and
at
down
the
the hillside,
riverbank, we're down
the
at
rows
water
run
level
along the
here,
hillside,
and we're
and
looking
that's
up the
intended
side
to
of the
slow down
riverbank. You
water
can see a
and
shovel
trap
for
erosion.
scale. So
We
this
see
riverbank
that
is
they
a
aren't
couple of
using
meters
the
tall.
whole hillside for
And
corn.
right
They
in the
have
upper part of the
divided the
riverbank, we see this
hillside
very
up into
dark
strips where
brown, almost
some
black
are
zone,
planted in corn,
and that is
some are
a dark,
planted
rich
in
topsoil that was the
grasses
surface of
and
the
other
floodplain
crops that conserve
before
agriculture.
Euro-Americans
The
settled this
streams
watershed
are
in the
preserved
1800s
with
and
riparian
converted it to
zones and
agriculture.
grassy
And then
strips along
above
them.
that black zone,
And so there's a
we
lot
see
of
this
practices
lighter
in this
brown
landscape
layer
to
that's
try to
really a
keep
couple
the
of feet deep,
eroded
at least
soil from
a
moving
foot or
off the
two deep.
landscape, and
That
trap and
is
hold it on
sediment
the
that
hill slope
washed
as much
off
as
the
possible.
hillsides from about the 1850s to the 1950s and was transported down and deposited over the floodplain as overbank deposition. So that is historical agricultural sedimentation as a result of the period of intensive agriculture in this landscape. So you can imagine this river system and its floodplain were pretty dramatically changed. And in fact, our watersheds and our river systems are probably really not in equilibrium now, because pretty much throughout the mid-latitudes we have done this major land cover change and changed dramatically the water runoff and the soil erosion and put our watersheds into disequilibrium, all within the last 200 to 300 centuries. In the American West, it's too dry for agriculture, but there have been impacts from humans from cattle grazing. And in particular, there are a lot of stream basins that have been cut by arroyos. So on the left, we see an unincised stream channel. It's a wet meadow, so there's a little channel flowing through here somewhere. It's really hard to see. It's not incised, it's up at the level of the floodplain, and in the springtime this whole meadow gets pretty wet, and you can see that the meadow is really completely occupied by sedges and forbs, and if we dug a soil pit in this meadow, we would see probably a rich, dark soil like we saw in the previous slide. On the right-hand side, we see a stream in central Oregon that probably had a meadow just like that, or very similar, up at this level. But starting sometime in the late 1800s, this stream channel incised and cut down, and currently it's flowing down here at this lower level below the meadow. And it's got a little new floodplain that it started down here at this lower level. Just for scale, here's a geomorphologist for scale walking down the hill slope. If you go back and look at this old flat valley floor that the channel has incised below, you'll see a really dark floodplain soil there that probably represents a wet meadow soil, something like this one we saw on the left. So cattle grazing has done some dramatic transformations like this. But climate change can do the same thing. If we look at these arroyos and look at their valleys, in some cases we can go back to this valley wall back here and we'll see old arroyos that were created thousands of years ago in the past and then completely filled up back to the valley floor level and disappeared, and the stream was back in an unincised state. So there are prehistorical episodes of arroyo cutting. We can't attribute them to agriculture. We can't attribute them to cattle grazing. They're probably due to climate changes in the past. Finally, urbanization has also affected sediment yields. This is an example. This is a figure that's basically the same as figure 712 in your textbook. And in this case, we're looking at sediment yield, again, tons per square mile, could be tons per square kilometer on the vertical axis. And on the horizontal axis, we're looking at time starting in the 1800s and moving to the right. And we're looking at an area in the eastern U.S. in the mid-Atlantic states. And we're looking at Euro-American agriculture coming in around 1800 and beginning to convert the forest to croplands. And what the curve shows is what appears to be the change in sediment yield as Euro-Americans came in and began to change the land cover, change the vegetation cover. Sediment yields increased and peaked with agriculture maybe around 1900, and then agriculture began to decline and conservation practices came in. But this watershed then was converted to an urban area in 1960. So it's actually on the far outskirts of Washington, D.C. and Baltimore, Maryland, and the city had grown out, and what was farmland became converted to suburbs in the 1960s. And by that point, they were measuring sediment yield. And so we see this really big spike in sediment yield around 1960, and then it declines. So what's going on here? Well, this big spike is the construction period. This is when roads are being built, lots are being put in, houses are being built, the land's very cleared. And then within a few years, those lots are planted with sod and trees, and the land cover comes back on the landscape and the sediment yield drops. And so this shows that urbanization also has effects on sediment yield, and the critical period for urbanization is the construction period, when the land is relatively bare and relatively disturbed. And just for scale, this shows us that the conversion from forest to agriculture increased sediment yield maybe 5 to 10 times, but the increase from urbanization was bigger than that. It was 20 times or more greater than over natural forest covers. Okay, that's the end of Part A of Lecture 9, and you want to go on to Part B to get the other 3 topics on this outline.